What is the definition? Topology generated by this means collection of subsets of X. Every element of A, there is basis element such that it contains X contain A. So this is nothing but what? Topology generated by basis. That means once you are given an open base, we can generate topology, right? Suppose you're given actually, suppose X equals to AB. Suppose this is my singleton A, singleton B. Yeah, it is always open base. Yesterday we checked. The question is, what is a topology generated by this? Means what? Already told you one technique. This is nothing but what? Union of a collection of union of all members of script beta. That means, what is the topology here? Union of all members. That means, suppose you take A, union A. What you're getting? You're getting singleton A. That means A. Suppose you're taking B in union with B. What you're getting? Singleton B. Right? And A union B. Take these two members. What is the union? A comma B. Right? And empty union means what? You're going to get empty. So what is this? Singleton A, singleton B. This is X. This is empty. You know, it is always open. It is always topology. You can check it. Empty and X are members of tau, and tau is closed with respect to finite intersection. Tau is closed with respect to arbitrary union. Therefore, it is a topology NX. This topology is known as topology generated by open base. Right? So this is a very important idea. So once you are given a open base, we can generate a topology. Right? Next is actually metric topology. Means once you are given a metric space, every metric space is a topological space. Once you are given a metric space, this metric induces a topology. This D induces a topology on X. This topology is nothing but actually induced topology or metric topology. Right? So what is the topology here? You know, suppose my script B is this, a collection of open balls. Connection of open balls. You know, what is my collection? Open balls. Open balls centered A, radius R. You know, it is actually open base. It's a basis for metric space X. Why? Because this is my metric space. Suppose you give me point, I can find an open ball around this. You give me Y, I can find an open ball around this. So first condition is satisfied. What is second condition? You give me two open balls which are intersection. I can find another open ball which is containing this. Right? So it's an open base. This open base, the topology generated by this is nothing but metric topology or induced topology. The topology generated by this. What is the definition of this? What is the definition of this? For any member you take, there exists a basis element which is containing X contained in A. Right? So for every member in A, there exists a basis element. What is a basis element? What is a basis element? Open ball. It's open ball, center at X. Open ball, this contains X contained in A. So this is nothing but a metric topology or induced topology. On metric space X. That means every metric space is a topological space. Right? Every metric space is a topological space. And next argument is comparison of two topologies. What is comparison? Suppose X is a set tau1 and tau2 are two topologies. So then tau1 and tau2 are comparable if or only if at least one of the topology which is inside other. Tau1 is contained in tau2 or tau2 is contained in tau1. Tau1 is weaker than tau2 or tau2 is weaker than tau1. At least one of them happens. So at least one of them happens, one can say that tau1 tau2 are comparable. So suppose you're given it two topologies. Suppose you're given it two topologies. You know it is a topology. This is also topology. Question is, are they comparable? No, because tau1 is not contained in tau2. Of course, tau2 is not contained in tau1. Why? Why tau1 not contained in tau2? Because singleton A is an open set in tau1, but singleton A does not belongs to tau2. Means the singleton A is an open set with respect to tau1. Singleton A is not open set with respect to tau2. Therefore, tau1 is not contained in tau2. Similarly, tau2 is not contained in tau1 because singleton B is an open set in tau2, but it's not open set in with respect to tau1. Therefore, they are not comparable. So this condition is not satisfied. So two topologies on a set may not be comparable. That's what my point, right? Two topologies. What is my notice? Two topologies on a set may not be comparable. May not be comparable, right? Suppose you are given indiscrete topology. What is indiscrete topology? Suppose my set is X. What is indiscrete topology? Empty and X. Indiscrete topology is always contained in cofinite topology. Yes or no? Because cofinite topology contains empty and X. Yes or no? So therefore, this is always subset of this. Therefore, these two topologies are comparable. Understand? You know, it is a proper. It is proper. Why? Because you take this A is a, suppose you can take for laws of general, you can take X equals to R. Suppose you take this R minus 1, 2, 3. You know, it is an open set with respect to cofinite topology, but it's not open with respect to indiscrete. Because the indiscrete topology, in indiscrete topology, there are only two open sets, empty and X. This is not an open set with respect to indiscrete. Therefore, this indiscrete topology is strictly weaker than cofinite topology. Strictly weakened. They are comparable, of course. They're indiscrete topology is strictly weaker than cofinite topology. Right? Similarly, cofinite topology is always contained in co-countable topology. Yes or no? This is strictly. Why? Because when you take an open set with respect to cofinite topology, what is the definition? Either A complement is full X or A complement is finite. Right? So any finite set is countable set. So therefore, A complement X or A complement is countable. That means what? A is a member in tau C. That means when you started with A is in tau F, that is an element in tau C. Therefore, cofinite topology is always contained in co-countable topology. This is strictly. Why? Because I can find an open set with respect to co-countable. Suppose you take A equals to R minus 1 to 3 going on. You know, it is an open set with respect to co-countable, but it's not open set with respect to cofinite. Therefore, it is strictly. There exists at least one open set with respect to co-countable, which is not open set with respect to cofinite. Therefore, it is strictly weaker than, tau F is strictly weaker than tau C. Right? And tau C is always contained in discrete topology. Because this is collection of all subsets. This is after all a collection of subsets whose complements are full X or whose complements are countable. So therefore, this is always subset of power set. Therefore, these two are comparable, these two are comparable, these two are comparable, these two are comparable. Right? Similarly, you take this one. Are they comparable? Suppose you take cofinite topology equals to R for laws of generality. Suppose you can take usual topology. Are they comparable on R? Are they comparable? The answer is yes. So this is strictly cofinite topology is strictly weaker than usual topology. Why? Because you start with any open set with respect to cofinite. So what is the definition? A complement should be finite. So for laws of generality, I can take A should not be empty. A should not be empty. So once A should not be empty. See, if A is empty, nothing to prove it. Yes or no? Understand the idea? If A is empty, If A is empty, empty is always empty belongs to usual topology, nothing to prove it. If A is non-empty, so it is non-empty means what? A complement should not be R. That means A is open set with respect to cofinite. Therefore, A complement should not be R means what? A complement should be finite. Right? What is cofinite topology? Cofinite topology means collection of subsets of R such that whose complement is full or whose complement is finite. Right? So therefore, if A is empty, nothing to prove it. Empty is always open set with respect to usual. So if A is non-empty, A complement should be not equals to R. So whenever A complement should not be equals to should not be equals to R, this condition fails. So automatically this condition is true because A is in tau F. So A complement is finite. So loss of generality, finite set means what? You can take a finite set x1, x2, xn. So without loss of generality, I can take they are in strictly order because they are real numbers. Real numbers satisfy trichotomic properties. So we can compare them. Right? So that means A complement is this. What is A set? What is A set? This is my x1, this is my x2, this is my xn. What is my A set? A set is to take the complement means x1, x2, xn complement. That means this is my A. What is this a complement of this? Minus infinity to this. X1 union x1 to x2 union going on. Xn minus 1 to xn union xn to infinity. Right? You know it is always open ray. It's an open set with respect to usual. It is open set with respect to usual. It is open set with respect to usual. It is open set with respect to usual metric, usual topology. It is open set with respect to usual topology. Arbitrary of open set is always open set. Therefore, it is open set with respect to usual topology. Right? So therefore, A is open set with respect to usual topology. Therefore, when you take A is an open, we have done that is an open with respect to usual. When you take A is open with respect to cofinite, which is non-empty, therefore A is open set with respect to usual. Therefore, in both cases, we have done it. Right? Which is why it is strictly weaker because you start with this open 0, 1. It is open set with respect to usual, but it's not open with respect to cofinite. Why? Because whose complement is what? Minus infinity closed 0, closed 1 to infinity. This is not a finite set. Therefore, this is strictly weaker than usual topology. Right? Similarly, so there is an important result actually. When you want to compare two topologies, suppose you are given two open bases, B and B dash are open bases for X. So these conditions are equivalent. This topology generated by open base is contained in topology generated by open base B dash if and only if you take any open basis element, take any element which is in open base, you take any element in open base bold B, I can find a basic open set with respect to B dash such that it is containing X which is contained in B, bold B. So when you want to show that two topologies comparable, you need to take a basic open set containing X. There exists another basic open set with respect to B dash such that this B dash contains X contained in B. So this is a very, very important result. Using this result, suppose you can take this. So before doing this, let us start with an example. Suppose you can take this X equals to R, suppose usual and lower limits. What is lower limit? What is lower limit? Anybody, what is lower limit? Just go back to your arguments. What is lower limit? Suppose you take this, we have seen that this is an open base. These are standard arguments. This is an open base for usual topology. Suppose you can take this. This is also open base for usual topology. Because I already told you this is an open base. We have done it yesterday. So this is also open base for usual topology. And we have seen that this is an open base for lower limit. For lower limits. Right? We have seen this. This is open base for this is the right limit topology, right? So suppose you can take this B equals to B1 union B minus K such that B belongs to B1, where K equals to 1 over N belongs to N, and B1 is equals to segments, open segments. Yes. This is an open base for a some topology. That topology, see, once you are given an open base, already told you, once you are given an open base, this generates some topology. This generates some topology and R. This topology is nothing but K topology. Understand? You are given an open base means what? That generates some topology. That topology is nothing but here usual topology. Once you are given an open base here, that basis generates usual topology. You can easily check it. So this is an open base we have seen yesterday. So this open base generates some topology. Thus topology is nothing but lower limit topology. This is an open base for topology, some topology. That topology is nothing but right limit topology. This yesterday we have seen that this is an open base for some topology. That topology is nothing but actually K topology, right? So using these arguments, of course, then there is another open base, right ray. Is it an open base for some topology? Yes, because when you give me X, I can find a open ray which is containing X. When you give me Y, I can find an open basic open set, which is containing Y. So this is first condition is true. What is my second condition? When you take two basic open sets, A comma infinity, of course you can take B comma infinity. So what is intersection? Intersection is always, what is this? This is in my intersection. So B1 intersection B2 is nothing but what? B comma infinity. So when you take any member which is in this, I find another basic B3. What is my B3? Same, B comma infinity. Understand? This is my intersection. In this case, this is my intersection. You take any point, I in the intersection, what is my B3? My B3 is B comma infinity, which is contained in B1 intersection B2. Why? B1 intersection B2 is nothing but B comma infinity only, right? Suppose you can take this situation. Suppose you can take B comma infinity. What is intersection? What is intersection? Anybody? This is my intersection. So B1 intersection B2 is here, A comma infinity. You take any element in this. What is my B3? B3 I can choose as B1 intersection B2 only. So therefore, all possible case true. Therefore, it is an open base. This open base for some topology, this topology is nothing but right ray topology. Anna. Similarly, this is my left ray this is my, again, this is also open base for some topology, the same condition. So this basis induces some topology. That means this basis generates some topology. This topology is nothing but what? Left ray topology. Now you have basis, and you have topologies. Now question is, suppose you are given usual topology, you are given lower limit topology. Question is, are they comparable? Are they? So is it true actually? Is it true? Which of them is true? Either this is contained in tau well or tau well is contained in tau u. Which one of is true? Usual topology is weaker than tau well because so what is my theorem tells you? My theorem tells you that, my property tells you that when you want something, you want to show that which is contained in tau b is contained in tau b dash, you take any basis element, and any element which you take in a basis element, I can find another basic open set with respect to another open base, which is containing X contained in this. This is true. So similarly here, you take any basic open set. What is a basic open set? Already told you what is the basic open sets here. What is my basic open sets? Usual topology. For usual topology, these are the basic open sets. Open A comma B. These are the open basic open sets. So you take any basic open set, you take any point which is in a basic open set. I need to find the basic open sets with respect to lower limit topology. What are the basic open sets with respect to lower limit topology? Left to closed, right open. Left to closed, right open. So question is, suppose you are taking on a basic open set with respect to usual, you take a point. Can you find a basic open set with respect to lower limit topology? Yes. We find a basic open set. This is my basic open set. This is my B dash. This is my B. Yes or no? So when you give me any element here, I can find a basic open set B dash is equals to closed B open B, closed X open B, which is containing X contained in B. So therefore, this is true for every X. Therefore, satisfying this property. Therefore, tau u is contained in tau. Is it clear? Because we have shown the result. So any basic open set you take, suppose you take this here y, suppose you take this a comma b, suppose you take y here. So can you find a basic open set with respect to lower limit topology? Yes, I find a basic open set which is containing y, contained in this set, contained in this set. You give me z, I can find a basic open set with respect to lower limit, which is contained in this basic open set. When you give me some r, I find a basic open set with respect to lower limit, which is contained in your basic open set. Therefore, this is true for every element. Hence, lower limit, this usual topology is contained in lower limit topology by argument. Similarly, the question is tau L is contained in tau u? The answer no. Because tau L is not contained in tau u. Why? Because you take this 1, 2. Is it a basic open set? Yes, it's a basic open set because it's in the form of left to close, right open. So once it is basic open set, right? Once it is basic open set, always which is in tau L because it is generated by B na. It is generated by this intervals. It is generated by this intervals. So it is in tau L. Question is it in tau u? Is it open with respect to usual topology? Is it open with respect to usual topology? The answer no. Because is it open with respect to usual? No, because one is not interior point, no. So can you find a basic open set? What are the basic open sets with respect to usual topology? The basic open sets with respect to usual topology are this one, this one. Open A, open B, A less than B, A comma B belongs to R. So the basic open sets are open bounded intervals, A comma B. Now my question, can you find a basic open set with respect to usual topology which is contained in this region? No, because left region is outside. Yes or no? This left region is outside. This red region, left region is outside. Therefore, I never find a basic open set with respect to usual which is contained in this one, which is contained in this one. Understand? Can you find a basic open set which is contained in this region? No, because this left to side region is outside of this. Therefore, it is not open set with respect to usual. Is it clear? Hello? Is it clear?
Okay.
Right. Suppose you can take this. This is my. We have seen that this is an open base, right? This is my open base. It induces right topology, right ray topology, right? Right ray topology, which are denoted by tau. This is my open base for usual topology. This induces usual topology, which are denoted by this. Question is tau is contained in tau u or tau u contained in tau 2? Tau? Are they comparable? Are they comparable? Are they
Yes,
comparable?
Yes.
Tau u contained in tau 1.
Tau u contained in
Tau.
Right ray.
How? Suppose you can take the basic open set. Suppose you find a basic open set. So this is a basic open set in this. So therefore, it is open set with respect to usual. Question is it open with respect to tau? Suppose 1/2 belongs to here. Question is, if in order to say that it's an open set with respect to tau, can you find suppose this is B dash. Can you find B dash which is in B dash such that which is containing 1/2 contained in open 0, 1? No, right? What are the elements in B dash? Right rays. If it is right ray, this is infinite interval, this is a bounded interval. So conduction. Understand? Is it clear? Understand? This is my open bounded interval containing 1/2. Can you find an open ray containing this? Can you find an open ray which is contained in this? See, this open ray, this outside of this, right? Right ray. This right side, right ray should not contain in this open bounded interval. Yes or no? This right ray should not contain in this bounded interval. ఇది bounded interval ఉంటుందా right ray? ఉండదు కదా.
ఉండదు
So therefore it's
No.
not open with respect to the right ray topology. Therefore this is not true. Is it true? Therefore this tau u is not contained in tau. Question is tau is contained in tau u? The answer is yes, because I start with the basic open set. What are the basic open sets with respect to right ray? These are basic open sets. Take a mind. Take any element. This is my basic open set. Take any element. I can always find a basic open set containing X containing this. I can find always basic open set. So this is my basic open set, which is contained in your B. This is my B. This is my B dash. Understand? My B is A comma infinity. What is my B dash? What is my B dash? Anybody? A comma X plus 1. So this is containing X contained in B. This is true for every X. Therefore satisfying the condition. Therefore this tau is contained in tau u. Is it clear? So they are comparable, but they are not equal. They are comparable, okay, at least one of them happens. Therefore they are comparable, but they are not equal. Right? Next is, suppose you can take a very strong example. Suppose you can take this. Suppose already I told you, you take any X equals to R. This is my open base. So this is my B1. What is my B? My B is B1 union B minus K such that B belongs to B1. You know, this induces a topology. You've seen this topology is called as K topology, which are denoted by tau K. Right? Next is lower limit topology. So you know, this is my left to close, right open. You know, this is open base. This open base induces a topology. This topology is called lower limit topology. This is denoted by tau. Question is, now my question is, tau is contained in tau L, tau K, or tau K contained in tau L? Which of them is true? Anybody? What is my K? K is equals to 1 by n. So tau L is contained in tau K, or tau K contained in tau L? So none of them is true, right? This is not true. Why? Because say, suppose you can take this closed 0, closed 1, 2, close open, closed 1, open 2. You know, this is a basic open set with respect to tau L. So therefore it is open set with respect to tau L. That means this is 1, 2 is in a open set with respect to tau L. Question is it open with respect to tau K? Is it true? Is it true? Is it open with respect to tau K? Anybody? Is it open? Yeah. Is it open? No, right? Suppose, you know, it is open with respect to tau K. What happens? I can find a basic open set contain. See, suppose you can take this is B, this is B dash. So I can find a basic open set with respect to B such that this is containing 1, this basic open set containing 1, this contained in 1, 2. But any basic open set with respect to K topology are of the form segments or segments minus K. Understand? You know, any basic open sets with respect to K topology, either segments or B minus K or segments minus K. This is segment. See, in Rudin, this notation is segment. According to Rudin, this notation is nothing but segment. Okay, segment or open bound intervals. Okay. So in the basic open sets, open bound intervals or open bounded intervals minus K. Open bound intervals minus K. So general game ఉండొచ్చు యూనియన్ అంటే ఓపెన్ బౌండెడ్ ఇంటర్వల్స్ కావచ్చు లేకపోతే ఓపెన్ బౌండెడ్ ఇంటర్వల్స్ మైనస్ K. ఇప్పుడు యాక్చువల్గా ఒకవేళ ఈ పాసిబిలిటీ తీసుకుంటే యాక్చువల్గా దిస్ 1 2 ఒకవేళ ఇది అయింది అనుకోండి ఏమొస్తుంది? this 1 belongs to here and 1 should be right side to 1. 1 should be right side to A. So ఈ కేసు తీసుకుంటే ఏమైతుంది? ఈ కేసు తీసుకుంటే ఏమైందమ్మా? This A is inside 1 2. So ఈ కేసు తీసుకుంటే ఏమైతుంది? A is right side to 1. Therefore A is less than 1. 1 is less than or equals to A. Therefore A less than A. So conduction. అసలు ఈ కేసు తీసుకుంటే ఫెయిల్ అయిపోయింది. ఏ కేసు తీసుకుంటే ఈ కేసు తీసుకుంటే ఫెయిల్ అయిపోయింది. సిమిలర్లీ ఈ కేసు తీసుకుంటే ట్రూ అయిద్దాం. సేమ్ ఐడియా. ఈ కేసు తీసుకున్నా కూడా సేమ్ ఐడియా. Conduction. You are getting the same conduction. Therefore, why you are getting conduction? You know, this is open with respect to tau k. If you assume that, then you are getting a conduction. Therefore, this is not open with respect to tau k. So therefore, there is at least one open set with respect to tau. Well, this is not open set with respect to k topology. So this is not contained in tau k. Right? Similarly, is it true? Tau k contained in tau l? Is tau k contained in tau l? Anybody? The answer no. Why? Because I can take A equals to -1 comma 1 minus K. You know, it is a basic open set. Basic open set with respect to tau k. So basic open set got automatic equal under the open set. Of course, K and endama, K and end 1 by n's. కదా? K లో 0 ఉందా? లేదు. K లో 0 లేదు కాబట్టి A లో 0 ఉంటుంది. Yes or no? Because this is -1 comma 1 లో 0 ఉంటుంది. K లో లేదు కాబట్టి 0 ఎక్కడ ఉంటుంది? A లో ఉంటుంది. Right? So therefore A is an open set with respect to tau k which is containing 0. Question is it open? Is it open with respect to lower limit topology? The answer, is it open with respect to lower limit topology? No. Why? Because if it is open, I can find a basic open set with respect to lower limit topology such that which is containing 1, which is containing 0, which is containing 0, which is containing, I can find a basic open set of this form which is containing 0, containing A. Right? Because this is open set with respect to lower limit topology. Therefore, left to close, right open. So A is contained in this means what? A should be less than or equals to 0, 0 less than B. Therefore, here B is positive. Therefore, by Archimedean property, we can choose a large n of n such that this 1 by n naught is less than B. But 1 by n is positive, and you know A less than or equals to 0. Therefore, 1 by n naught should be in A comma B. 1 by n naught should be in A comma B means what? It should be in close to A open B. Whenever 1 by n naught is here, therefore that 1 by n naught should be in A by this argument, by star. But the thing is, what is A? Actually, A is nothing but -1 comma 1 minus K. So which is absolutely conduction, because what is my A? A is nothing but set of all real numbers lying between -1 to 1, excluding 1 by n's. Excluding 1 by n's. So conduction, because 1 by n naught is in actually A. Is absolutely wrong, because A is what? A is nothing but set of all real numbers lying between -1 to 1, excluding 1 by n's. So conduction. Therefore, we are getting conduction. It is open with respect to tau l is wrong. Therefore, our argument is wrong. Therefore, it is not open with respect to tau. Therefore, tau k is not containing tau. Is it clear? Hello?
Yes.
Yes? Yeah. Going to finish this. Yeah. Next is, suppose you can take same thing, x equals to r. Suppose my open base is open A comma is A less than B. You know, it is an open base for usual topology. This generate usual topology. This is my B union B minus K. This the B belongs to B1. Sorry, B1. What is my B1? Segments. What is my K? K is nothing but 1 by n. You know, this generated topology. This topology is nothing but K topology. Question is, are they comparable? Is it contained in tau k, or tau k is contained in tau u? Are they comparable? So this is always true, right? This is always true. Why? Because what are the basic open sets? Anybody? What are the basic open sets in usual topology? This one. What are the basic open sets in K topology? Either A comma B or either A comma B or look at it. Either A comma B or A comma B minus K. A comma B minus K. Question is, now you can take this. Suppose your basic open set is like this. Right? Right? So automatically, when you take a basic open set which is containing X, I can choose basic open set in tau K as itself. This is my B. What is my B dash? B dash is itself B. This is open set with respect to tau K. Therefore, there exists a basic open set with respect to tau K. This B is nothing but what? B. B is contained in B. B is contained in itself. Therefore, when you give me X in this basic open set with respect to usual, I can find a basic open set with respect to K topology, which is containing X contained in B. So when this is true for every X. This is true for every X. See, ఇక్కడ basic open set మీరు రిప్లేస్ చేయాలనుకోండి, నేను basic open set with respect to K topology ఏమి ఇస్తాను? ఇదే ఇస్తాను. సరిపోద్ది కదా? మీరు ఇది ఇస్తే సేమ్ మీ basic open set మళ్ళీ అదే ఇస్తాను. So therefore, automatic ఏమైతే this is contained in tau K. Question is tau K is contained in tau U? The answer no. Same argument. Suppose you can take A equals to minus 1 comma minus K. It is an open set with respect to tau K, which is containing 0. Question is it open with respect to usual? The answer no. Suppose it is open with respect to usual, I can find a basic open set with respect to usual such that which is containing 0 contained in A. So by the same argument, by argument property, we are getting a conversion. Same strategy. So therefore, this is not contained in this. Therefore, this is not contained in this. This is not contained. Therefore, they are not comparable. Right? Next is continuous function. So before continuous function, go for subbases. Subbase, open subbase. Open subbase or in subbase in one first, it is subbases. Subbases means, of course, it is a collection of subsets of X. Whenever X is a non-empty set, X is a set. It is said to be subbases. Open subbases or subbase. According to Munkar, subbases. According to Simmons, open subbase. For a topological space, if only, a collection of finite intersections of script S form an open base. Correct. See, if అన్ని ఇంటర్సెక్షన్ చేశారనుకోండి, అంటే ఏంటి, అన్ని ఇంటర్సెక్షన్ చేశారనుకోండి, ఫైనైట్ ఇంటర్సెక్షన్, అది ఓపెన్ బేస్ కావాలి. అండర్స్టాండ్? అన్ని ఫైనైట్ ఇంటర్సెక్షన్ చేశారనుకోండి, అది ఓపెన్ బేస్ కావాలి. అప్పుడు యాక్చువల్గా ఆ కలెక్షన్ ఏమంటాం? ఓపెన్ సబ్ బేస్ అంటాం. సబ్ ఎగ్జాంపుల్, you can take X equals to R. Suppose my collection is this race. My collection is race. Left ray, right ray. Question is it an open subbase? Is it an open subbase? Open subbase for R? The answer is because మీరు ఏదైనా A less than, suppose A, B are real numbers. A, ఇన్ఫినిటీ నేమ్ అని చెప్పాను, ఫైనైట్ ఇంటర్సెక్షన్ చేయాలి. ఫైనైట్ ఇంటర్సెక్షన్ చేస్తే బేసిక్ ఓపెన్ సెట్ రావాలి కదా. సో పాసిబిలిటీస్ ఏంటి? దిస్ ఇస్ మై A, సపోజ్ A, ఇన్ఫినిటీ. B ఒకవేళ ఇక్కడ ఉందనుకోండి, వాట్ ఈస్ ఇంటర్సెక్షన్? ఎనీబడి? దిస్ ఇస్ 1, this one. What is intersection?
AB.
This is a basic open set with respect to usual. So it's an open set. Right? So when do you say this? A less than B. Similarly, if A equals to B, what is intersection? If A equals to B, there is no intersection, empty. So in this case, empty set is open set with respect to usual. Yes or no? If A equals to B, A, infinity, intersection with minus infinity, comma A. What is intersection? Empty. Empty is always open set with basic open set with respect to usual. Next is, if you take A bigger than B, what is A bigger than B? What is intersection? B, comma A. See, this is minus infinity, comma A. This is B, comma infinity. What is intersection? B comma A. So this is also basic open set with respect to user. Therefore, to take any possible finite intersections, you're going to get a basic open sets. Therefore, this form a open base, open subbase. From, right? Suppose you can take this x equals to R2, right? What is my open base? Open rectangles or open circles. It's an open base. Yesterday we've seen open base. Open bases or open base for R2. We have seen yesterday. Of course, open circles, open rectangles also, open subbase for R2. Now my question is, what is open subbase? Open subbase is race, means strips. What are strips? R cross. You know, this is like minus infinity comma infinity. Union minus infinity comma infinity cross R. Strips. This is always open base. Why? Because see, what is my subbasic open sets here? What is my subbasic open sets? Strips. This R cross minus infinity comma infinity. That means what? Not R cross, sorry. A comma B. You can take bounded intervals. You can take bounded intervals. A comma B cross R. A comma B cross R. Union R cross C comma D. So this type of intervals. These are strips. This A comma B. This is my strip. This is my strip. This is the first strip 1. Horizontal, vertical strip. This is what? Vertical strip. Horizontal strip. So what is the intersection? Anybody? This is an open rectangle. So it is a basic open set for R2. So hence it is a open subbase for R2. Right? So finite intersection, if you do the finite intersection of members of script is, if you get a basic open set, then that collection is nothing but open subbase. That is an idea. Right? If you take any finite intersections, if you get an open base, so basic open set, then that collection is nothing but open subbase. Right? If you give me open subbase, same strategy. If you give me any collection you take, suppose you give me any S, suppose you give me A, B, C, D, suppose you can take this. Suppose you give me any collection, this induces a topology. Why? Because what is my open subbase? Already told you, finite intersections. A collection of all finite intersections. Finite intersections of members of script is. What are the finite intersections? Anybody? Singleton A intersection, singleton A. What is intersection? Singleton A. Singleton B intersection, singleton B. What is intersection? Singleton B. Right? Suppose A intersection B. What is intersection? Empty. Empty intersection. The in this form. X. It's an open base. It's an open base for X. What is the topology? Anybody? What is the topology induced by this? In terms of Japan, union of all members of script beta. What are unions? Singleton A, singleton B, empty, X. Union AB. So this is my open. This is a topology. So this topology is generated by B, or this topology generated by S. So once you give me any collection, one can generate a topology. This topology is nothing but topology generated by S, or topology generated by script bit. Right? So this is nothing but open subbase. Maybe chala chesukochu. So this is nothing but open subbase. Next is continuous function. What is meant by continuous function? You start with any topological space. You have seen a continuous function with respect to metric. So what is meant by continuous function? So let us start with two topological spaces. Right? A function from x to y is continuous. Before now, inverse image of open set is open. Inverse image of open set is any open set in Y is open in X. If this is true, one can say that F is continuous. Suppose you take any open set G, look at its inverse image. If it is open in X, then one can say that it is a continuous function. If this is true for every G. Look at any open set in X, Y, look at its inverse image. If it is open set in X, then that is nothing but a continuous function. And suppose you can take a constant function. Every constant function is continuous. Why? Because you take any constant function defined by f of x is equals to y naught for every x belongs to x, where y naught is a fixed element in y. Is it continuous? Answer yes, because you take this is my x, this is my y, right? This is my open set. You take any open set. What is my y naught? Y naught is here. There are two possibilities. Y naught is not contained here. Not see this G does not contain y naught, or G is inside y naught. Y naught is not contained in G, or y naught is contained in G. There are two possibilities. So look at its inverse image. G is open set in Y. We have taken. What is inverse image definition? Set of all elements in X such that whose image belongs to G. Already I told you there are two possibilities. If y naught is in G, this is my y naught. If y naught is in G, what are the inverse images? Every x satisfying this condition. Every x in X satisfying this condition. Therefore, what is inverse image? Full X. Whenever y naught is not in G, y naught is not in G, what is inverse image? No x satisfy this condition. Therefore, empty. So X is inverse image. There are two possibilities, either X or empty. So X is always open set in X because X is topological space. Empty set is always open set in X. Empty set and X are always open set in X. Therefore, inverse image of any open set is open set. Hence, it is a continuous function. So any constant function is always a continuous function. No doubts. Right? Suppose you can take this set of all. F is a function from here to here. We have seen already this idea. Suppose you can take mod x. Is it continuous? Yes, it is continuous. You know, it is a metric space. It is a metric space. It's a modulus. Modulus graph is always continuous function, right? But according to topology, there are two ways actually. So whenever f is continuous, if only inverse image of open set is open set. Open is open. Second is inverse image of basic open set is open. Inverse image of basic open set is open, or else inverse image of subbasic open set is open. We move same amount in topology, right? So I'm going to check this inverse image of basic open set is open. What are the basic open sets in R? We've seen A comma B. A comma B is a basic open set. This is my modulus, right? Basic open. This is my basic open set with respect to usual topology. Question is, what is inverse images? There are two possibilities. There are so many possibilities. Suppose you A here, B here. What is inverse images? This is minus A. This is minus A. This is minus B. This is B. So what is inverse image? Anybody? Inverse image is minus B comma minus A union A comma B. Whenever A is bigger than positive. A is bigger than positive and A is less than B. Right? A is less than B. Suppose take the another version. Suppose your A is below 0. Right? B is here. What is inverse image? Minus B, B. So for A, there is no preimage. So what is inverse image? Minus B comma B. Whenever A less than 0, B positive. Suppose B is in outside, B less than 0. What is inverse image? No inverse image. There is no line which is parallel to x-axis meeting this line, this curve. Therefore, there is no preimage. So in all cases, you know, this is a basic open set in usual topology. See, this is basic open set in usual topology, right? So therefore, this is open set, basic open set in usual topology. Therefore, always open set. This basic open set in usual topology, this open set. Union of open set is always open set, therefore it is open. Similarly, this is basic open set in usual topology, always open set with respect to usual topology. It's open set with respect to usual topology. Therefore, inverse image of basic open set is always open set, hence it is continuous. Right? Suppose you can take this f of x is equals to x square. Is it continuous? Yes, because it's a polynomial parabola. We have seen that it's a metric space, it's a metric space. It's a polynomial is always continuous because it satisfies sequential criteria for continuity. Xn converges to x, that will imply that f of xn converges to f of x. That is one version. What the second version is, you take a basic open set here. Look at its inverse image. Suppose A is here, B is here. What is inverse image? Minus root 2a. This is root a. This is minus root b. This plus root b. So what is inverse image? Inverse image is minus root b minus root a union root a root b. Whenever a positive, a less than b. Whenever a is below 0, whenever a is below 0, this may be, what is the inverse image? Minus root b plus root b. Right? Whenever a less than 0, b positive. Whenever a b is outside, b outside means what? A is outside. So there is no image for a and b. What is the inverse image? And so it is basic open set with respect to usual. It is basic open set with usual. Union of open set is always open. This is a basic open set with respect to usual. It is always open. The empty is always open. So in all cases, it's open. So inverse image of basic open set is open. Hence it is continuous. Right? Suppose you can take any function with respect to discrete is always continuous. Any function with respect to discrete topology from another topological space is always continuous. Why? Because take any open set in this topological space. Take any open set. Look at its inverse image. Inverse image is always subset of x. So this is my x. This is my y. This is my g. Look at its inverse image. Inverse image is always subset of x. Any subset of x is always open set with respect to discrete. Therefore, inverse image of open set is open set. Therefore, hence it is continuous. So any function from discrete topological space to any topological space is always continuous. Is it clear? Hello? Hello? Are you there?
Yes, sir. Yes, sir.
Right? Suppose you can take this. Any function from any space to indiscrete is always continuous. Is always continuous. Why? Because what are open sets in indiscrete? Empty and x. What is inverse image of empty? Empty. Empty is always open set in x. What is inverse image of x? Inverse image of x? Y. X. Sorry. Inverse image. This is y, kada? This is y. So what is inverse image of y? X. By set theory. So x is always itself is open set. So inverse image of any open set, empty open తీసుకుంటే empty వచ్చింది, y తీసుకుంటే x వచ్చింది. Empty and x are always open sets in x. Therefore, inverse image of any open set is always open set, hence it is continuous. Is it clear? Hello? Yeah. So with this I conclude continuity and open base updates. Actually గా మీకు థింగ్ ఏంటంటే యాక్చువల్గా ఈ మెట్రిక్ స్పేసెస్ టోపాలజీలో చాలా లెస్ నెంబర్ ఆఫ్ క్వశ్చన్స్ ఉన్నాయి జైల్లో. రైట్? ఇంతవరకు చదివితే సరిపోతుంది. యాక్చువల్లీ మీ సిలబస్ ఇంతవరకే ఉంది. రైట్? మీ సిలబస్ సిఎస్ఆర్ పాయింట్ ఆఫ్ లో మొత్తం లేదు. రైట్? జేఎల్డిఎల్లో జనరల్ ఓన్లీ ఓపెన్ బేస్, ఓపెన్ సబ్ బేస్, కంటిన్యూటీ వరకే ఉంది. సో ఇంతవరకు స్టాప్ చేస్తున్నాను లెక్చర్. రైట్? ఎనీ డౌట్స్?
సో ఒకటి నాన్ స్పేస్ మీద ఏం చెప్పలేదు సార్.
నామినల్ స్పేస్ ఫంక్షన్ ఆన్సర్స్ లో వస్తుంది.